This presentation is delivered by the Stanford Center for Professional Development.
Okay, good morning. Welcome back to the third lecture of this class. So here's what I want to do today. And some of the topics I'll do today may seem a little bit like I'm jumping from topic to topic, but here's sort of the outline for today and the logical flow of ideas. In the last lecture, we talked about linear regression, and today I want to talk about sort of an adaptation of that called locally weighted regression. It's actually a very powerful algorithm that's actually one of my former mentors' probably favorite machine learning algorithm. We'll then talk about the probabilistic interpretation of linear regression and use that to move on to our first classification algorithm, which is logistic regression. Take a brief digression to tell you about something called the perceptron algorithm, which is something we'll come back to again later this quarter. And time allowing, I hope to get to Newton's method, which is an algorithm for fitting logistic regression models. So let's just recap what we're talking about in the previous lecture. Remember the notation I defined was that I used this x superscript I, y superscript I to denote the ith training example. And when we're talking about linear regression or ordinary least squares, we use this to denote the predicted value output by my hypothesis h on the input xi. And my hypothesis was parameterized by the vector parameters theta. And so we said that this was equal to sum from theta j xij. Written more simply as theta transpose x. And we had the convention that x subscript 0 is equal to 1. So this accounts for the intercept term in our linear regression model. And lowercase n here was the notation I was using for the number of features in my training set. Okay, so in the example, we're trying to predict housing prices. If we had two features, the size of the house and the number of bedrooms, we had two features and little n was equal to 2. So just to finish recapping the previous lecture, we defined this quadratic cost function, j of theta equals 1/2 sum from I equals 1 to m of theta of xi minus yi squared, where this is a sum over our m training examples in my training set. So lowercase m was the notation I've been using to denote the number of training examples I have, or the size of my training set. And at the end of the last lecture, we derive the value of theta that minimizes this in closed form, which was x transpose x inverse x transpose y. Okay. So as I move forward in today's lecture, I'll continue to use this notation. And again, I realize there's a fair amount of notation to all remember. So if partway through this lecture you forgot, if you're having trouble remembering what lowercase m is or what lowercase n is or something, please raise your hand and ask. When we talked about linear regression last time, we used two features. One of the features was the size of the house in square feet, so the living area of the house, and the other feature was the number of bedrooms in the house. In general, when you're out there applying machine learning algorithms to some problem that you care about, the choice of the features will very much be up to you, right? And the way you choose your features to give the learning algorithm will often have a large impact on how well it actually does. So just for example, the choice we made last time was x1 equals to the size, and let's leave aside the other feature of the number of bedrooms for now. Let's say we don't have data that tells us how many bedrooms are in these houses. One thing you could do is actually define. Oh, let's draw this out. And so, right. So let's say that was the size of the house, and that's the price of a house. So if you use this as a feature, maybe you get, theta 0 plus theta 1 x1, this sort of linear model. If you choose, we'll just copy the same data set over. Right? You can define a set of features where x1 is equal to the size of the holes, and x2 is the square of the size of the holes. Okay, so x1 is the size of the house in, say, square footage, and x2 is just take whatever the square footage of the house is and just square that number, and this would be another way to come up with a feature. And if you do that, then the same algorithm will end up fitting a quadratic function for you, theta 2 x1 squared. Okay, because this is actually x2. And, depending on what the data looks like, maybe this is a slightly better fit to the data. You can actually take this even further. Oops. Right? Which is, let's see, I have 7 training examples here. So you can actually maybe fit up to a 6th order polynomial. You can actually fit a model theta 0 plus theta 1 x1 plus theta 2 x squared plus up to theta 6 x to the power of 6, and fit a 6th order polynomial to these 7 data points. And if you do that, you find that you come up with a model that fits your data exactly. Because with, I guess, in this example I drew, we have 7 data points, and so if you fit a 6th order polynomial, you can sort of fit a line that passes through these 7 points perfectly. And you probably find that the curve you get is, well, look, maybe something like that. And on the one hand, this is a great model in the sense that it fits your training data perfectly. And on the other hand, this is probably not a very good model in the sense that, none of us seriously think that this is a very good predictor of housing prices as a function of the size of the house. Right? So we'll actually come back to this later. It turns out, of the models we have here, I feel like maybe the quadratic model fits the data best, whereas the linear model, it looks like looks like there's actually a bit of a quadratic component in this data that the linear function is not capturing. So we'll actually come back to this a little bit later and talk about the problems associated with fitting models that are either too simple, use too small a set of features, or the models that are too complex and maybe use too large a set of features. Just to give these a name, we call this the problem of underfitting. And very informally, this refers to a setting where there are obvious patterns, or where there are patterns in the data that the algorithm is just failing to fit. And this problem here we refer to as overfitting. And again, very informally, this is when the algorithm is fitting the idiosyncrasies of this specific data set. Right? It just so happens that of the 7 houses we sampled in Portland or wherever you collect data from, that house happened to be a bit more expensive, that house happened a little less expensive. And by fitting a 6th order polynomial, we're sort of fitting the idiosyncratic properties of this data set rather than the true underlying trends of how housing prices vary as a function of the size of the house. Okay? So these are 2 very different problems. We'll define them more formally later and talk about how to address each of these problems. But for now, I hope you appreciate that there is this issue of selecting features. So if you want to choose features for learning problems, there are a few ways to do so. And we'll talk about feature selection algorithms later this quarter as well. So automatic algorithms for choosing what features to use in a regression problem like this. What I want to do today is talk about a class of algorithms called non-parametric learning algorithms that will help to alleviate the need somewhat for you to choose features very carefully. Okay. And this will lead us into our discussion of locally weighted regression. Let me just define the term. Linear regression, as we've defined it so far, is an example of a parametric learning algorithm. And parametric learning algorithm is one that's defined as an algorithm that has a fixed number of parameters that's fit to the data. Okay? So in linear regression, we had a fixed set of parameters theta, right, that was fit to the data. In contrast, what we're going to talk about now is our first non-parametric learning algorithm. The formal definition, which is not very intuitive, so I'll replace this with a second something more intuitive. The sort of formal definition of a non-parametric learning algorithm is that it's an algorithm where the number of parameters grows with m, with the size of the training set. And usually it's defined as that number of parameters grows linearly with the size of the training set. This is the formal definition. A slightly less formal definition is that the amount of stuff you need, the amount of stuff that your learning algorithm needs to keep around will grow linearly with the training set. Or another way of saying is that this is an algorithm that will need to keep around an entire training set even after learning. Okay, so don't worry too much about this definition, but what I want to do now is describe a specific non-parametric learning algorithm called locally weighted regression. Which also goes by a couple of other names. Which also goes by the name LOESS for sort of historical reasons. LOESS is usually spelled L-O-E-S-S, sometimes spelled like that too. I'll just call it locally weighted regression. So here's the idea. And this would be an algorithm that allows us to worry a little bit less about having to choose features very carefully. So for my motivating example, let's say that I have a training set that looks like this. Okay, so this is X and that's Y. If you run linear regression on this, and you fit maybe a linear function to this, and you end up with a more or less flat straight line, which is not a very good fit to this data. You can sit around and stare at this and try to decide what other features to use, right? So maybe you want to toss in a quadratic function, but this isn't really quadratic either. So maybe you want to model this as a x plus x squared plus maybe some function of sine of x or something. You can actually sit around and fiddle with features. And after a while, you can probably come up with a set of features that are modeled as okay. But let's talk about an algorithm that you can use without needing to do that. So if now, suppose you want to evaluate your hypothesis H at a certain point, at a certain query point lowercase x. Okay, and let's say you want to know what's the predicted value of y at this position for x, right? So for linear regression, what we were doing was we would fit theta to minimize sum over I yi minus theta transpose xi squared and return theta transpose x. Okay, so that was linear regression. In contrast, in locally weighted linear regression, I'm going to do something slightly different. I'm going to look at this point x, and then I'm going to look at my data set and take into account only the data points that are sort of in a little vicinity of x. Okay, so I'm going to look at where I want to validate my hypothesis. I'm going to look only in the vicinity of this point where I want to evaluate my hypothesis. And then I'm going to take, let's say, just these few points. And I will apply linear regression to fit a straight line just to this subset of the data. Okay. I'm using the term subset. Well, let's come back to that later. So if I take this data set and I fit straight line to it, maybe I get, I don't know, a straight line like that. And what I'll do is then evaluate this particular value of straight line, and that would be the value I return from my algorithm. Okay, this would be the predicted value for this would be the value that my hypothesis outputs in locally weighted regression. Okay. So let me go ahead and formalize that. In locally weighted regression, we're going to fix theta to minimize sum over I to minimize that, where these terms W superscript I are called weights. And there are many possible choices for weights. I'm just going to write one down. So that's e to the minus xi minus x squared over 2. And so let's look at what these weights really are, right? So notice that suppose you have a training example xi, so that xi is very close to x. So if this is small, right, then if xi minus x is small, so if xi minus x is close to 0, then this is e to the minus 0, and e to the 0 is 1. So if xi is close to x, then wi will be close to 1. In other words, the weights associated with the ith training example will be close to 1 if xi and x are close to each other. Conversely, if xi minus x is large, then, I don't know, what would wi be? 0, right? Close to 0. Cool, right? So if xi is very far from x, then this is e to the minus of some large number, and e to the minus some large number will be close to 0. Okay. So the picture is, if I'm querying at a certain point x, shown here on the x-axis, and if my data set, let's say look like that, then I'm going to give the points close to this a large weight and give the points far away a small weight. And so for the points that are far away, wi will be close to 0. And so it's as if for the points that are far away, they will not contribute much at all to this summation, right? So think of this as sum over I of 1 times this quadratic term for close by points plus 0 times this quadratic term for far away points. And so the effect of using this weighting is that locally weighted linear regression fits a set of parameters theta, paying much more attention to fitting the points close by accurately, whereas sort of ignoring the contribution from far away points. Okay?
Yeah, why isn't exponentially decaying?
Yeah, let's see. So it turns out there are many other weighting functions you can use. It turns out that there are different communities of researchers that tend to choose different choices by default. There is a somewhat of a literature on debating what function to use. This sort of exponential decay function just happens to be a reasonably common one that seems to be a reasonable choice for many problems. But you can actually plug in other functions as well. Just to mention, one side comment to that. For those of you that are familiar with the normal distribution or the Gaussian distribution, I'm going to say this formula that I've written out here, it cosmetically looks a bit like a Gaussian distribution, okay? But this actually has absolutely nothing to do with Gaussian distributions. So this is not it's not that, probability of xi is Gaussian or whatever. This is no such interpretation. This is just a convenient function that happens to be a bell-shaped function, but don't endow this with any Gaussian semantics. Okay? And so in fact, well, if you remember the familiar bell-shaped Gaussian, again, it's just the weights you end up associating with these points is that if you imagine putting this sort of bell-shaped bump centered around the position of where you want to evaluate your hypothesis H, then this is saying this point here, I'll give a weight that's proportional to the height of the Gaussian, to the height of the bell-shaped function evaluated at this point. And the weight I'll give to this point will be, to this training example, will be proportional to that height, and so on. Okay? And so training examples that are really far away get to very small weight. One last small generalization to this is that normally there's one other parameter to this algorithm, which I'll denote as tau. Again, this looks suspiciously like the variance of a Gaussian, but this is not a Gaussian. This is a convenient form of function. This parameter tau is called the bandwidth parameter. And informally, it controls how fast the weights fall off with distance. Okay, so just copy my diagram from the other slide, I guess. So if tau is very small, if that's a query x, then you end up choosing a fairly narrow Gaussian, a fairly narrow bell shape, so that the weights of points that are far away fall off rapidly. Whereas if tau is large, if tau is large, then you end up choosing a weighting function that falls off relatively slowly with distance from your query. Okay, so I hope you can therefore see that if you apply locally weighted linear regression to a data set that looks like this, then to ask what your hypothesis's output is at a point like this, you end up fitting a straight line, making that prediction. To ask what your hypothesis output is at that value, you fit a straight line there, and you predict that value. And it turns out that every time you try to evaluate your hypothesis, every time you ask your learning algorithm to make a prediction for how much a new house costs or whatever, you need to run a new fitting procedure and then evaluate this line that you fit just at the position of the value of x, or the position of the query where you're trying to make a prediction. Okay? But if you do this, for every point along the x-axis, then you find that locally weighted regression is able to trace out this sort of very nonlinear curve for a data set like this. Okay? So in the problem set, we're actually going to let you play around more with this algorithm. So I won't say too much more about it here. But before I move on to the next topic, let me check what questions you have. Yeah.
It seems like you'd still have the same problem with overfitting and underfitting. Like when you have to choose tau. Like if you make it too small, then you're...
Yes, absolutely, yes. So locally weighted regression can run into... Locally weighted regression is not a panacea for the problem of overfitting or underfitting. You can still run into the same problems with locally weighted regression. What you just said about... And so some of these things I'll leave you to discover for yourself in the homework problem. You actually see what you just mentioned.
It almost seems like you're not even building a model with this locally weighted. You need all the data that you originally had anyway. So
Yeah.
I'm just trying to think of it. Almost seems like you're manipulating the original data points.
Right. So the question is sort of just it's almost as if you're not building a model because you need the entire data set. And the other way of saying that is that this is a non-parametric learning algorithm. And so this is I don't know. I won't debate whether are we really building a model or not. But this is a perfectly fine. So if I think when you write code implementing locally weighted linear regression on on the data set, I think of that code as a whole as building your model. So we actually use this. We've actually used this quite successfully to model the dynamics of autonomous helicopter, for instance. Yeah.
The variance of this algorithm that learn the weight based on the data?
Learn what weights? Oh, the weights WI.
Instead of using the exponential.
I see, yes. So it turns out there are a few things you can do. One thing that's quite common is how to choose this bandwidth parameter tau, right, as using your data. We'll actually talk about that a bit later when we talk about model selection. Is one last question?
Why do you stress on the fact that WI is not Gaussian? Because if you add the constants, then you can make it Gaussian and then...
Oh, I guess, let's see, boy. The weights are not random variables, and is not, for the purpose of this algorithm, is not useful to endow it with probabilistic semantics. So you could choose to define things as Gaussian, but it doesn't lead anywhere. In fact, it turns out that I happen to choose this bell-shaped function to define my weights. It's actually fine to choose a function that doesn't even integrate to 1, that integrates to infinity, say, as your weighting function. And so in that sense, you know, I mean, you could force it in the definition of a Gaussian, but it's sort of not useful, especially since you use other functions that integrate to infinity and don't integrate to 1. Okay, last question. I should move on.
Assume that we have a very huge set of data, for example, very huge set of houses, and we want to predict the level for each house. So we should run the algorithm for each input, and I think it is very costly.
You're absolutely right. So because locally weighted regression is a non-parametric algorithm, every time you make a prediction, you need to fit theta to your entire training set again. So you're absolutely right. If you have a very large training set, then this is a somewhat expensive algorithm to use, because every time you want to make a prediction, you need to fit, you know, a straight line to a huge data set again. Turns out there are algorithms that turns out there are ways to make this much more efficient for large data sets as well. So I don't want to talk about that. If you're interested, look up the work of Andrew Moore on KD trees. So figured out ways to fit these models much more efficiently. That's not something I want to go into today. Okay, let me move on. Let's take more questions later. So, okay. So that was locally weighted regression. Remember the outline I had, I guess, at the beginning of this lecture. What I want to do now is talk about a probabilistic interpretation of linear regression. Right? And in particular, it'll be this probabilistic interpretation that lets us move on to talk about logistic regression, which would be our first classification algorithm. So, let's put aside locally weighted regression for now. We just talk about ordinary, you know, unweighted linear regression. And let's ask the question of why least squares, right? Of all the things we could optimize, how do we come up with this criteria for minimizing the square of the error between the predictions of the hypotheses and the values y predicted? So why not minimize, you know, the absolute value of the errors, or the errors to the power of 4 or something? What I'm going to do now is present one set of assumptions that will serve to, quote, justify why we're minimizing the sum of squares error. Okay. It turns out that there are many assumptions that are sufficient to justify why we do least squares, and this is just one of them. So you know, just be clear, I'll present one set of assumptions under which least squares regression makes sense, but this is not the only set of assumptions. So even if the assumptions I described don't hold, least squares actually still make sense in many circumstances. But this will maybe help, you know, give one rationalization, like one reason for doing least squares regression. And in particular, what I'm going to do is endow the least squares model with probabilistic semantics. And so let's assume in our example of predicting housing prices that the price of the house is sold for is going to be some linear function of the features plus some term epsilon I. Okay, and epsilon I will be, our error term. You can think of the error term as capturing unmodeled effects, like that maybe there are some other features of a house, like maybe how many fireplaces it has, or whether there's a garden or whatever, that there are additional features that we just failed to capture. Or you can think of epsilon as random noise. Okay? So epsilon is our error term that captures both these unmodeled effects, just things we forgot to model. Maybe the function isn't quite linear or something, as well as random noise, like maybe that day the seller was in a really bad mood, and so he sold it. He just refused to go for a reasonable price or something. And now I will assume that the errors have a probabilistic have a probability distribution. I'll assume that the errors epsilon I are distributed, right? This tilde denotes epsilon I is distributed according to a probability distribution. That's a Gaussian distribution with mean 0 and variance sigma squared. Okay, so I'm going to use script n here. N stands for normal, right, to denote the normal distribution, also known as the Gaussian distribution, with mean 0 and covariance sigma squared. Actually, just quickly raise your hand if you've seen a Gaussian distribution before. Okay, cool. Most of you. Great. Almost everyone. So, in other words, the density for Gaussian, as most of you have seen this before, the density for epsilon I would be 1 over root 2 pi sigma e to the negative epsilon I squared over 2 sigma squared. Right? And the density for epsilon I will be this bell-shaped curve with, with one standard deviation being sort of sigma. Okay. This is formula for that bell-shaped curve. So let's see. So erase the board. So this implies that the probability distribution of a price of a house, given xi and the parameters theta, that this is going to be Gaussian with that density. Okay? Another way of saying this is that the price of a house, given the features of the house and the parameters theta, this is going to be a random variable that's distributed Gaussian with mean theta transpose xi and variance sigma squared. Right? Because we imagine that the way the housing price is generated is that the price of a house is equal to theta transpose xi and then plus some random Gaussian noise with variance sigma squared. And so the price of a house is going to have mean theta transpose xi and variance sigma squared. Right? Does this make sense? Can you raise your hand if this makes sense? Yeah, okay, most of you. In point of notation, oh yes.
We don't know anything about the error. Why do you assume here error is a Gaussian?
Right. So, boy, yeah. So part of the what is it? Why do I assume the error is Gaussian? Two reasons, right? One is it turns out to be mathematically convenient to do so, and the other is I don't know. I could also mumble about justifications, such as things of the central limit theorem. It turns out that for the vast majority of problems, if you apply a linear regression model like this and try to measure the distribution of the errors, not all the time, but very often you find that the errors really are Gaussian, that this Gaussian model is a good assumption for the error of in regression problems like these. Some of you may have heard of the central limit theorem, which says that the sum of many independent random variables will tend towards a Gaussian. So if the error is caused by many effects, like the mood of the seller, the mood of the buyer, some other features that we miss, whether the place has a garden or not, and if all of these effects are independent, then by the central limit theorem, you might be inclined to believe that the sum of all of these effects will be approximately Gaussian. But in practice, I guess the two real answers are that one, in practice, this is actually a reasonably accurate assumption, and two, it turns out to be mathematically convenient to do so. Okay. Yeah?
It seems like we're saying if we assume the error around our model has zero mean, then the error is centered around our model, which it seems almost like we're trying to assume what we're trying to prove.
Let's delay to what I'm trying to prove. But yes, we are assuming that the error has zero mean, which is, yeah, right. I think maybe, I suspect later this quarter we'll get to some of the other things. But so for now, just think of this as a mathematical, it's actually not an unreasonable assumption. I guess, in machine learning, all the assumptions we make are almost never true in the absolute sense, right? Because for instance, housing prices are priced to dollars and cents, and so the error will be, errors in prices are not continuous value random variables because houses can only be priced at a certain number of dollars and a certain number of cents, and you never have fractions of cents in housing prices, whereas a Gaussian random variable would. So in that sense, assumptions we make are never, quote, absolutely true, but for practical purposes, this is a accurate enough assumption that it'll be useful to make it. Okay. Maybe I think in a week or two we'll actually come back to say a bit more about the sorts of assumptions we make and when they help our learning algorithms and when they hurt our learning algorithms. We'll do that. We'll say a bit more about when we talk about generative and discriminative learning algorithms, like in a week or two. Okay. So let's just point out one bit of notation, which is that when I wrote this down, I actually wrote P of yi given xi and then semicolon theta. And I'm going to use this notation when we are not thinking of theta as a random variable. So in statistics, this is sometimes called the frequentist point of view, where we think of there as being some sort of true value of theta that's out there that's generating the data, say. But we don't know what theta is, but theta is not a random variable. Right? So it's not like there's some random value of theta out there. It's that there's some true value of theta out there. It's just that we don't know what the value of theta is. So if theta is not a random variable, then I'm going to avoid writing P of yi given xi comma theta, because this would mean the probability of yi conditioned on x and theta. And you can only condition on random variables. So at least for this part of the class where we're taking sort of a frequentist viewpoint rather than a Bayesian viewpoint, in this part of the class we're thinking of theta not as a random variable, but just as something we're trying to estimate. I'll use the semicolon notation. And so the way to read this is the probability of yi given xi and parameterized by theta. Okay, so you can read the semicolon as parameterized by. And the same way here I'll say yi given xi parameterized by theta is distributed Gaussian with that. All right. So then we're going to make one more assumption. We're going to assume that the error terms are IID, okay, which stands for independently and identically distributed. So this is going to assume that the error terms are independent of each other. Right? the identically distributed part just means that I'm assuming they all come from the same Gaussian distribution with the same variance. But the more important part of this is I'm assuming that the epsilon i's are independent of each other. Now, let's talk about how to fit a model. The probability of y given x parameterized by theta. I'm actually going to give this another name. I'm going to write this down. I'm going to call this the likelihood of theta as the probability of y given x parameterized by theta. And so this is going to be the product over my training set that, which is in turn going to be a product of those Gaussian densities that I wrote down just now. Okay. Again, in point of notation, I guess, I defined this term here to be the likelihood of theta. And the likelihood of theta is just, the probability of the data y, right, given x and parameterized by theta. The terms likelihood and probability are often confused. And so the likelihood of of theta is the same thing as the probability of the data you saw. And so likelihood and probability are sort of the same thing, except that when I use the term likelihood, I'm trying to emphasize that I'm taking this thing and viewing it as a function of theta. Okay? So so likelihood and probability, they're really the same thing, except that when I want to view this thing as a function of theta holding x and y fixed, I'll then call it the likelihood. Okay? So hopefully you hear me say the likelihood of the parameters and the probability of the data, right? Rather than likelihood of the data or probability of parameters. So I try to be consistent in that terminology. So given that the probability of the data is this, and this is also the likelihood of the parameters, how do you estimate the parameters theta? So given a training set, what parameters theta do you want to choose for your model? Well, the principle of maximum likelihood estimation says that you can choose the value of theta that makes the data as probable as possible. Right? So choose theta to maximize the likelihood. Or in other words, choose the parameters that make the data as probable as possible. Right? So this is maximum likelihood estimation from statistics. It says choose the parameters that makes it as likely, as probable as possible for me to have seen the data I just did. And so, for mathematical convenience, let me define lowercase l of theta. This is called the log likelihood function, and it's just log of L of capital L of theta. So this is log of product over I 2 pi sigma e to the that, and I won't bother to write out what's in the exponent for now. It's just same as from the previous board. Log of the product is the same as the sum of the logs, right? So this is sum of the logs of which simplifies to m times 1 over root 2 pi sigma plus, and then log of exponentiation cancel each other, right? So log of e of something is just whatever's inside the exponent. So, you know what? Let me write this on the export. minus okay. So maximizing the likelihood, maximizing the log likelihood is the same as minimizing that term over there. Oops. Well, you get it, right? Because there's a minus sign. So maximizing this, because of the minus sign, is the same as minimizing this as a function of theta. And this is, of course, just the same quadratic cost function that we had last time, j of theta. Right? And so what we've just shown is that the ordinary least squares algorithm that, that we worked out in the previous lecture is just maximum likelihood assuming this probabilistic model, assuming IID Gaussian errors on our data. Okay. One thing that we'll actually revisit in the next lecture, notice that the value of sigma squared doesn't matter, right? That somehow, no matter what the value of sigma squared is, and sigma squared has to be a positive number, it's the variance of a Gaussian. So, but no matter what sigma squared is, so long as it's a positive number, the value of theta we end up with will be the same, right? So because minimizing this, you get the same value of theta no matter what sigma squared is. So it's as if in this model, the value of sigma squared doesn't really matter. And we'll just remember that for the next lecture. We'll come back to this again. Any questions about this? Actually, let me clean another couple of boards and I'll see what questions you have. Questions? Yeah.
Yeah, I think here you try to measure the likelihood or niceness of theta by a function of error. But yes. I think it's not a good measure because it depends on the family of theta too. For example, if we have a lot of parameters, we have problems with overfitting.
Yeah. I think you're asking about overfitting, whether this is a good model. I think the things you're mentioning are maybe deeper questions about learning algorithms that will come back to this. That will come back to later. So don't really want to get into that right now. Yeah. Other questions? Yeah. Okay. So this endows linear regression with a probabilistic interpretation. And I'm actually going to use this sort of probabilistic interpretation in order to derive our next learning algorithm, which will be our first classification algorithm. Okay. So you recall that I said that regression problems are where the variable y that you're trying to predict is continuous valued. Now I'm actually going to talk about our first classification problem, where the value y you're trying to predict will be discrete value. It can take on only a small number of discrete values. And in this case, I'll talk about binary classification, where y takes on only 2 values, right? So you come up with classification problems if you're trying to do, say, medical diagnosis and try to decide, based on some features, if a patient has a disease or does not have a disease. Or if in the housing example, maybe you're trying to decide, will this house sell in the next 6 months or not? And the answer is either yes or no, right? It'll either be sold in the next 6 months or it won't be. Other standard examples, if you're trying to build a spam filter, is this email spam or not? Is yes or no? Or if some of my colleagues are interested in predicting whether a computer system will crash. So, have learning algorithm to predict, will this computing cluster crash within the next 24 hours? And again, it's a yes or no answer. So that's X, that's Y. And so in the classification problem, Y takes on two values, 0 and 1, let's say, in binary classification. So what can you do? Well, one thing you could do is take linear regression, as we've described it so far, and apply it to this problem. Right? So given this data set, you can fit a straight line to it. Maybe you get that straight line. Right? But this data set I've drawn, right, is an amazingly easy classification problem. It's pretty obvious, to all of us that, right, the relationship between X and Y is, well, you just look at a value around here, and if it's to the right, Y is 1, and if it's to the left, then Y is 0. So apply linear regression to this data set, and you get a reasonable fit, and you can then maybe take your linear regression hypothesis, the straight line, and threshold it at 0.5. And if you do that, you sort of get the right answer. You predict that if X is to the right of sort of a midpoint here, then Y is 1, and if X is to the left of that midpoint, then Y is 0. So some people actually do this, apply linear regression to classification problems. And sometimes it'll work okay. But in general, it's actually a pretty bad idea to apply linear regression to classification problems like these. And here's why. Let's say I change my training set by giving you just one more training example all the way out there. Right? Imagine if, given this training set, it's actually still entirely obvious what the relationship between X and Y is. Right? It's just take this value, it's greater, then Y is 1. If it's less, then Y is 0. And by telling you, that by giving you this additional training example, it really shouldn't change anything. I mean, I didn't really convey much new information. There's no surprise that this corresponds to Y equals 1. But if you now fit linear regression to this data set, you end up with, I don't know, maybe a line that looks like that. Right? And now the predictions of your hypothesis have changed completely if you threshold your hypothesis at Y equals 0.5. Okay? So
in between there might be an interval where it's 0 again, right? That far out point.
Oh, you mean like that?
Right.
Yeah, fine. Yeah, sure. I'll give you a data set like that. So same thing. Right. So I guess this is just, yes, you're right, but this is an example, and this example works too.
That would change it even more.
Oh.
If you gave it all those things.
Yeah, then I think this actually make it even worse. We actually get a line that pulls down even further. Right? So this is my example. I get to make it whatever I want, right? but the point of this is that there's no deep meaning to this. The point of this is just that it could be a really bad idea to apply linear regression to a classification problem. And sometimes it'll work fine, but usually I wouldn't do it. So there are a couple of problems with this. One is that, well, so what do we want to do for classification? If you know the value of Y lies between 0 and 1, then to try to fix this problem, let's just start by changing the form of our hypothesis so that my hypothesis always lies in the unit interval between 0 and 1. Okay? So if I know Y is either 0 or 1, then let's at least not have my hypothesis predict values much larger than 1 or much smaller than 0. And so I'm going to, instead of choosing a linear function for my hypothesis, I'm going to choose something slightly different. And in particular, I'm going to choose this function. H subscript theta of x is going to be equal to g of theta transpose x, where g is going to be this function. And so this becomes 1 over 1 plus e to the negative theta transpose x. Okay. And g of z is called the sigmoid function and is often also called the logistic function. It goes by either of these names. And what g of z looks like is the following. So on the horizontal axis, I'm going to plot z. And so g of z will look like this. Okay, I didn't draw that very well. Okay, so g of z tends towards 0 as z becomes very small, and g of z will asymptote towards 1 as z becomes large, and it crosses the vertical axis at 0.5. So this is what the sigmoid function, also called the logistic function, looks like. Yeah, question?
Why choose a sigmoid and not a step function?
Say that again?
Why we cannot choose a step function? Isn't like that's better the binary?
Yeah, let me come back to that later. So it turns out, where did I get this function from, right? How did I mean, I just wrote down this function. It actually turns out that there are two reasons for using this function that we'll come to. One is when we talk about generalized linear models, we'll see that this falls out naturally as part of a broader class of models. And another reason that we'll talk about next week is, well, it turns out there are a couple of, I think, very beautiful reasons for why we choose the logistic function. So we'll see that in a little bit. But for now, let me just define it and just take my word for it for now that this is a reasonable choice. Okay. But notice now that the values output by my hypothesis will always be between 0 and 1. And furthermore, just like we did for linear regression, I'm going to endow the outputs of my hypothesis with a probabilistic interpretation. Right? So I'm going to assume that the probability that y is equal to 1, given x and parameterized by theta, that's equal to h subscript theta of x. Right? So in other words, I'm going to imagine that my hypothesis is outputting all these numbers that lie between 0 and 1. I'm going to think of my hypothesis as trying to estimate the probability that y is equal to 1. Okay. And because y has to be either 0 or 1, then the probability that y equals 0 is going to be that. All right. So more simply, it turns out, actually take these two equations and write them more compactly. I'm going to write p of y given x, parameterized by theta. This is going to be h subscript theta of x to the power of y times 1 minus h of x to the power of 1 minus y. Okay? So I know this looks somewhat bizarre, but this actually makes the derivation much nicer. So if y is equal to 1, then this equation is h of x to the power of 1 times something to the power of 0. So anything to the power of 0 is just 1, right? So if y equals 1, then this is something to the power of 0, and so this is just 1. And so if y equals 1, this is just saying p of y equals 1 is equal to h subscript theta of x. And in the same way, if y is equal to 0, then this is p of y equals 0 equals this thing to the power of 0, and so this disappears. This is just 1 times this thing to the power of 1. Okay? So this is a compact way of writing both of these equations together into one line. So let's talk about parameter fitting, right? And again, we can ask, well, given this model of my data, how do I fit the parameters theta of my model? So the likelihood of the parameters is, as before, it's just the probability of data, right? Which is product over I, p of yi, given xi, parameterized by theta, which is just plugging this in. Okay, and I dropped this theta subscript just so you can write a little bit less. Oh, excuse me. These should be xi's and yi's. So, as before, let's say we want to find the maximum likelihood estimate of the parameters theta. So we want to find a setting of the parameters theta that maximizes the likelihood L of theta. It turns out that very often, just when you work out the derivations, it turns out that it's often much easier to maximize the log of the likelihood rather than maximize the likelihood. And so the log likelihood L of theta is just log of capital L. This will therefore be sum of this. Okay, and so to fit the parameters theta of our model, we'll find the value of theta that maximizes this log likelihood. Yeah. Say it again.
Why I is given to find?
Oh yes, thank you. Thanks. So how do you maximize this function? Well, it turns out we can actually apply the same gradient descent algorithm that we learned. That was the first algorithm we used to minimize the quadratic function. Remember, when we talked about least squares, the first algorithm we used to minimize the quadratic error function was gradient descent. And so we can actually use exactly the same algorithm to maximize the log likelihood. And you remember that algorithm was just you repeatedly take the value of theta and you replace it with the previous value of theta plus a learning rate alpha times the gradient of the cost function, the log likelihood, with respect to theta. Okay. One small change is that because previously we were trying to minimize the quadratic sum of the quadratic error term, today we're trying to maximize rather than minimize. So rather than having a minus sign, we have a plus sign. So this is just gradient descents, but for maximization rather than minimization. And so we actually call this gradient ascent. It's really the same algorithm. So to figure out what this gradient, so in order to derive gradient descent, what you need to do is compute the partial derivatives of your objective function with respect to each of your parameters theta I, right? So, and it turns out that if you actually compute this partial derivative, so if you take this formula, this L of theta, which is, got that wrong too. If you take this lowercase L of theta, if you take the log likelihood of theta, and if you take this derivative, take this partial derivative with respect to theta I, you find that this is equal to, let's see. Okay, and I don't know, the derivation isn't terribly complicated, but in the interest of sort of saving you watch me write down the cover of Blackboard's full of math, I'll just write down the final answer. But the way you get this is just take this, plug in the definition for x subscript theta as a function of xi, and take derivatives and work through the algebra. And it turns out it'll simplify down to this formula. Okay? And so, what that gives you is that gradient ascent is the following rule. Theta j gets updated as theta j plus alpha times this. Okay. Does this look familiar to anyone? Did you remember seeing this formula at the last lecture? Right. So when I worked out Bash gradient descent for least squares regression, I actually wrote down exactly the same. I actually wrote down exactly the same thing. Or maybe there was a minus sign and this was also flipped. But I actually had exactly the same learning rule last time for least squares regression. Right? So, I don't know, is this the same learning algorithm then? So what's different? How come I was making all that noise earlier about least squares regression being a bad idea for classification problems, and then, you know, I did a bunch of math and I skipped some steps, but I'm sort of claiming that you end up with really the same learning algorithm.
Very nice. Logistic functions.
Say that again?
Hypothesis is
Right. Okay, cool.
that's logistic.
Right, exactly, right. So as Yonchen is saying, this is not the same, right? And the reason is, in logistic regression, this is different from before, right? The definition of this H subscript theta of xi is not the same as the definition I was using in the previous lecture. And in particular, this is no longer theta transpose xi. This is not a linear function anymore. This is a logistic function of theta transpose xi. Okay? So even though this looks, you know, cosmetically similar, even though this looks similar on the surface to the Bash gradient descent rule I derived last time for least squares regression, this is actually a totally different learning algorithm. Okay? And it turns out that it's actually no coincidence that you ended up with the same learning rule. We'll actually talk a bit more about this later when we talk about generalized linear models. But this is one of the most elegant results of generalized linear models that we'll see later, that even though we're using a different model, you actually ended up with, you know, what looks like the same learning algorithm. And there's actually no coincidence. Cool. One last comment as part of a sort of learning process. Over here, you know, I said I take the derivatives and I ended up with this line. I didn't want to make you sit through a long algebraic derivation, but later today or later this week, please do go home and look at the lecture notes where, you know, I wrote out the entirety of this derivation in full, and make sure you can follow every single step of how we take partial derivatives of this log likelihood to get this formula over here. Okay. By the way, for those of you that are interested in seriously mastering machine learning material, when you go home and look at the lecture notes, it'll actually be very easy for most of you to look for the lecture notes and read through every line and go, yep, that makes sense, that makes sense, that makes sense, that makes sense, and sort of say, okay, cool, I see how you get this line. You want to make sure you really understand the material. My concrete suggestion to you would be to go home, read through the lecture notes, and check every line, and then to cover up the derivation and see if you can derive this yourself. Right? So in general, that's usually good advice for studying technical material like machine learning, which is if you work for a proof, if you think you understood every line, the way to make sure you really understood it is to cover it up and see if you can rederive the entire thing yourself. This is actually a great way for, I did this a lot when I was trying to study various pieces of machine learning, theory and various proofs. And this is actually a great way to study, which is cover up the derivations and see if you can do it yourself without looking at the original derivation. Okay. All right. I probably won't get to Newton's method today. I just want to take one quick digression to talk about one more algorithm, which was this question sort of alluding to this earlier. Which is the perceptron algorithm, right? So I'm not going to say a whole lot about the perceptron algorithm, but this is something that we'll come back to later this quarter when we talk about learning theory. So, in logistic regression, we said that G of Z output, my hypothesis output values that were real numbers between 0 and 1. The question is, what if you want to force G of Z to output either 0 or 1, right? So the perceptron algorithm defines G of Z to be this. So the picture is, or the cartoon is, rather than the smooth sigmoid function, you know, g of z now looks like the step function that you're asking about earlier. And same as before, we can use h subscript theta of x equals g of theta transpose x. Okay, so it's actually everything is exactly the same as before, except that g of z is now the step function. It turns out there's this learning rule called the perceptron learning rule that's actually even the same as stochastic gradient ascent for logistic regression. And the learning rule is given by this. Okay, so it looks, you know, just like the gradient ascent rule, or really the stochastic gradient ascent rule for logistic regression. So this is a very different flavor of algorithm than least squares regression and logistic regression. And in particular, because it outputs only values that either 0 or 1, it turns out it's very difficult to endow this algorithm with probabilistic semantics. And this is, again, even though, excuse me, right there, okay. And even though this learning rule looks cosmetically very similar to what we have for logistic regression, this is actually a very different type of learning rule than the others that we've seen in this class. And so, because this is, you know, so it's such a simple learning algorithm, right? Just compute theta transpose x and then you threshold and you output 0 or 1. This is relatively simpler algorithm than logistic regression, I think. And when we talk about learning theory later in this class, the simplicity of this algorithm will let us come back and use it as a building block. Okay, but that's all I want to say about this algorithm for now.